These are electrolytic capacitors. Electrolytic capacitors are used in power supplies to filter the DC voltage. They have the ability to store an electrical charge, and that's what makes them useful in that application. Most electrolytic capacitors are polarized. They'll have a positive terminal and a negative terminal. You really want to observe that polarity, because if you connect them backwards and apply voltage, they could react quite violently. They could start venting fluids and gases, and they will be destroyed very quickly, could even explode. Since they can hold a charge for an extended period of time, even after the power has been removed from the equipment in which they're installed, they can be dangerous. This one here has a working voltage of 400 volts DC, 470 microfarad, which is quite large. That can, a good capacitor can hold a charge for up to a number of days after the power has been removed. So you really want to discharge those before you go and work on the equipment, or replace the capacitor, or even do any testing. What I've done up to this point is I've used this piece of wire. It's essentially a piece of wire with a 10K resistor in series and an alligator clip on each end. I hooked it up to a capacitor to discharge it, and when I put both clips on, what it does is it shorts the capacitor through the 10K resistor and discharges it. And it works. It's simple, it's reliable, and it works. The downside, of course, is that there's no indication of any voltage remaining on the capacitor. There's no indication that you've actually discharged it. It's just a dumb piece of wire with a resistor in it. There's an interesting channel on YouTube called Mr. Carlson's Lab. Mr. Carlson's published a video on his Patreon site where he designs and constructs a capacitor discharger, a much more sophisticated one than this one, that shows you that it's worked and that it's working, and that the capacitor has been discharged and is safe to handle. Inspired by that video, I decided to design my own using parts I have on hand, and incorporating additional features I think would be useful for me. And this is what I came up with. This is the circuit of my capacitor discharger. They're a pair of probes. These probes are connected to the capacitor to be discharged. There's a couple of resistors. They're 15K, 50 watt resistors in parallel. That gives you a parallel resistance of 7.5K. That's 7.5 kiloohms. And they are directly connected to the probes. That's what discharges the capacitor. The rest of the circuit is for my indicators. There are two indicators. There's an LED and a panel meter. Now, resistors are not polarized, so they don't really care which way you hook them up. But panel meters and LEDs, of course, are polarized. So what I did was I incorporated a full wave bridge rectifier using 8 pieces of 1N4007 diodes, and use that to rectify the voltage across the resistors, which is across the capacitor, and gives me a positive bus here and a negative bus here, and that's what powers my indicators. The first indicator, of course, being the panel meter. It's a 0 to 1 milliamp panel meter that I bought probably 20 years ago, but it's new in box. I'd never used it for any projects. And I put it in series with a 1 megohm 2-watt resistor. Now we're going to have up to 1,000 volts here that we're going to be measuring. So 1 megohm in series with the meter with 1,000 volts applied will give us 1 milliamp, which is a full-scale reading. So this 0 to 1 milliamp meter now becomes a 0 to 1 kilovolt meter. The rest of the circuit is for powering an LED. Here's the LED, and essentially it glows when there's voltage applied. There are a pair of 68K 2-watt resistors in series with a 4.7 volt Zener diode. That Zener diode clamps the voltage across the LED. The LED has a series resistor of 249 ohms. It's just a half-watt resistor. I used 249 ohms because I have a whole reel of them. I used 68K resistors in series because I have a whole reel of them too. And these values are not critical. You can use a 220 ohm resistor or 270 ohm, it'll work just as well. And the Zener diode, if you have a 5 volt Zener, anything around 4.7 to 5.6 volts should work just as well. So those are the two sides of the circuit, the unknown and the DC side. So once I've designed the circuit, the next thing I usually do in a project like this is I go looking for an enclosure or a case of some sort. Many years ago I bought this ICO 1100 resistance substitution box on eBay. It didn't work. I opened it up and I'd found that somebody had tried to repair it and replace some of the resistors, but they damaged the switches beyond repair. The contacts were broken off of the phenolic, and so it was not repairable. So, but the case itself was perfect. Has no cracks, not even any scratches. It's a nice thick Bakelite case. It's in great shape. So I decided to use that. I got a piece of double-sided copper-clad board and cut it to exactly the same size as the front panel for the ICO substitution box, and drilled holes in the corners and started with that. This is the front panel. This is our panel meter, 0 to 1 kilovolt. There's our LED, and there are the jacks for our probes. This is the main circuit board here. You can see the diode bridge with the 8 1N4007 diodes. This is the 2 megohm resistor for the panel meter, and the Zener diode, and the 249 ohm resistor. The back of the circuit board contains the 268K 2-watt resistors because they stand off from the circuit board and they would interfere with the side of the case if they were soldered on the other side. The two 15K resistors that actually do the discharging are here, and they're connected in parallel using 14 gauge wire that's directly wired into the jacks, probe jacks. The applied voltage is taken to the input of the bridge up here by those two red wires. This is the LED down here, and it's held in place with goop. Now I used a different construction technique that I'd never used before. Because everything is made of double-sided copper-clad board, I just solder tacked using my soldering gun the board to the front panel, and it seems to be holding really well. I mean, it's very strong. Time will tell, but I'm quite confident that this is going to be a good solution. I'd never done this before, so to prepare this, I thought I would have to solder a bead all the way across, but it turned out I didn't have to. So what I had done is I'd used solder to tin the front panel, but it turns out it wasn't necessary to do that all the way along. I just tacked the corners, and this thing is really strong. It's not going anywhere, so it should stand up quite well. And it also stiffens the front panel. So this fits in here. I've got some nice shiny screws that I use, put in the corners. I've got rubber feet on the bottom and on the back, so I can use it either way. And there's just one more test I wanted to perform before we put this in service on our bench. This is called a high pot tester. It applies a high voltage between the current carrying parts of a device and the chassis or the enclosure. And if it finds there is any leakage between the current carrying devices and the enclosure, it sounds an alarm. You can adjust the voltage that it uses. You can adjust the test voltage, and I'm going to adjust it here for 1250 volts, because in Canada where I live, that's the standard for a 1-second test. So when you push the button, it will apply 1250 volts for 1 second, and if the unit passes, nothing will happen. If the unit fails, the alarm will sound. So I'll just plug in the ground return, and I'm going to connect it to the chassis. I'm going to connect the test lead to the current carrying wire that connects to the resistors in the probe. I'm going to plug that in. Now I'm not going to hold on to this because 1250 volts is a little too much for me. So I'm just going to put that on the bench, and I'm going to push the button to test it. There, we passed the test. Nothing happened. We'll do it again. 1250 volts for 1 second, and we passed. So there was no leakage between the current carrying parts of the circuit and the chassis itself. Now, in case you're curious, I'll show you what happens when it finds there's leakage. I will connect these two leads together and just let them drop there. And I'm going to push the test button. Now this is going to make some noise, so please either cover your ears or turn your volume down or hit the mute button. Okay, here we go. 3, 2, 1. That's what happens when you fail the test. It's good that it's loud because you've got a problem and you really can't ignore it. So that's all the testing that we need to do. I'm going to put the instrument in its case and put it on the bench. So just to show you that this works, I'm going to get a regular 9-volt battery. I mean, normally we'll be working with hundreds of volts, but not 9 volts. And just show you that the LED does light when I put it across terminals, either direction. So it's not, there's no polarity. I don't know if you can see that on the camera or not. The voltmeter does move very slightly. It's difficult to see that, but it does work. And I just stuck a label on there saying kilovolts. So down to 9 volts and you get an indication that there's voltage there, which is more than sensitive enough. I've connected a high voltage 0 to 400 volt power supply to the capacitor. We're going to charge it up. The voltmeter is connected right across the capacitor, and it's measuring the DC volts across the capacitor. The capacitor discharger is connected to the negative, well, to one side. One terminal of the capacitor discharger is connected to the negative pole of the capacitor. The other test lead, I will connect it to the positive terminal of the capacitor once it's charged up, and we'll be able to read the voltage. It should come up to about 400 volts there. So we're charging the capacitor up. We're at 150 volts, 200 volts. $300. Okay. 405 volts across the capacitor. Now, I'm not going to disconnect that yet. I'm just going to read the voltage here and watch that the LED lights up. So we'll just put that probe across there. As you can see, the LED is lit up, and the voltage reads approximately 400 volts. We just lost our negative lead here, so I'm going to turn off that high voltage. And I'm going to reconnect it. Reconnect the negative lead. Okay, we're back to normal. So it's draining off. We have 360 volts across the capacitor. I'm going to short it out again with the capacitor discharger. And we're seeing that the voltage is dropping very rapidly. Capacitor is discharging. The LED from where I stand, it's still lit, and we're down to, there we go. The LED's gone out. We're down to 2 volts. It's now safe to handle that capacitor, or to replace it, or to work on the circuit that it's connected to. So we can try that again. Okay, we have 400 volts. Oops. We have 405 volts across the capacitor. It reads 400. I'm going to remove the positive lead from the power supply. I just removed the positive lead from the power supply. And you can see that the voltage is coming down. So I guess that took about 15-20 seconds to discharge completely. So that's it. Thank you, Mr. Carlson, for the inspiration to build this. This is going to be on my bench. Now the last thing I did was I made up a test lead set. Just plugs in there. Now I can use any test leads I want separately, but I wanted something that I could keep with it attached permanently on my bench. So I made them not too long, and they're made of really flexible lamp cord. I did test this with the high pot tester, and it passed this assembly. And this way I don't have to, I can discharge capacitors, and I don't have to connect a separate meter, and I don't have to fumble around looking for test leads. They're already here, and it takes up very little space on my bench. And there it is. So ready to rock and roll.